Yeah, hello. Yeah, welcome back. Hello. Yeah, I started recording. Okay. Hello. Are you there? Hello. Yeah, are you with me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes,
Yeah,
sir.
yeah,
Yes,
yeah,
sir.
yeah,
Yes, sir. Yes, sir.
yeah, 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 yeah. Yeah, let's start and just in half an hour, let's have that. Yeah, right. So yeah, it's like more of generic, as I mentioned. No, this one, most of them like because since we are using the systems and also whatever the things I'm just covering, so it appears to be like very very much intuitive, and you try to interpret okay, nicely. And yeah, coming to the yeah yeah, as you see the role, or you can say that the moment once you try to define the operating system, there is no, like as I mentioned, there is no very crisp or like very well defined the definition for that, because it varies that depending upon where you are using. Like from the user perspective, it has certain objectives, and from a hardware perspective, it has certain objectives, and based on the computing environment, it has a different objectives. Like for example, in case of distributed systems, or like embedded systems, or like your personal computer, mobile devices, or the mainframes. So it has its own way of dealing the things. So therefore, there is no like a very crisp or accepted definition for that. But what is operating system? So if when you say that, so one way is that actually the operating system is that, suppose when you buy an operating system, you will get somebody like you will get a CD from the parcel. So that CD, you can say that is it the operating system? No, it contains the lots of system programs or lots of application programs will be there to assist the user for using that particular operating system and all. So therefore, one way you can say that the what is operating system means, it's a program, one program that runs most of the time, that runs all the time in a computer. It's not to be a kernel. It's not to be kernel. That means if you see operating system CD, for example, where it contains lots of other system programs, and along with that there is one executable code. It's known to be kernel. So that is the actual operating system and all, where which supports the various application programs to the underlying hardware and all. So you can say that the kernel can be viewed as an operating system where it's executable that is present, and along with that we have some supporting various application programs will be there. And so this can be viewed as something like sometimes it's kernel, and I can say that sometimes the operating system. These words are we are using interchangeably in this part of this course and all. So we can say that the kernel can be viewed as an operating system at a very low level and all, right? So, and then yeah, coming to the before going to that, let us know that actually how the operating system starts functioning in the computer and all. So when you switch on the computer, when you powered on the computer, the first thing is that you have a bootstrap program. That means the very initial program. So that will be loaded into the memory and all. So that particular bootstrap program that used to be present in this ROM, that means read-only memory. That means in a computer we have a ROM or EEPROM. So where these bootstrap program are not a very initial program, the first program that used to be running on the CPU will be the bootstrap program. So that used to be first loaded by reading from the read-only memory to a main memory, and then it runs it is run by the CPU, and then that initializes all aspects of the system under computer system. It means that it initializes various other peripherals, and that it will keep initialize the maybe the device driver, not device drivers, the device controllers, maybe initializing their registers and so on. And then it also loads the operating system. It also loads the operating system and starts execution and all. So when the computer just started, that means here the first program, that's not to be a bootstrap program, it used to be present in the ROM. So it will be first brought into it will be placed, or it will be written into the memory, and it starts executing. So the execution of the bootstrap program is nothing but the initial setting up the registers and other things, like initializing the registers at a device, different peripherals, or even in the CPU and other things, and then it loads the operating system. It loads the operating system from the disk to the main memory and all. Because operating system, the size may be large. So, and it cannot be on the main memory. And another thing is that the main memory is the volatile one. Volatile one. That means the moment once you power off, the contents will be erased. So again, when you power on, again there won't be any contents at all. It's just refreshed mode. So then you need to brought in whatever the programs you want to execute. So therefore, at the beginning, when a computer startup, you have a bootstrap program. So it will be loaded from the ROM to the main memory. And then this bootstrap program will be executed. As part of execution, it initializes all aspects of the system. And then it loads the operating system and to the kernel. And once the operating system is loaded, then the operating system program will start running. And then it will the user programs will be brought into the memory. Then it will be execution will take place and all. So this is the way the initial part of the when the computer just powered on. So that is the way the operating system will be loaded into the main memory using the bootstrap program. And then, yeah, this is the broader organization of a computer. As you mentioned, it contains the CPU, I have a memory, and you have different peripherals and all. And you can say that now the CPU, it may contains, like earlier it have only one CPU, general purpose. And nowadays, actually, like any machine, it contains like more than one CPU, like a dual core, quad core, octa core. We have multiple CPUs are present. Then you have different peripherals are there, and for each peripheral, for controlling those peripheral or for accessing those peripherals and all, you have the corresponding device controllers will be there. Suppose, for example, you have a hard disk and you have a corresponding disk controller, and you have the peripherals that are connected to USB. So you have a USB controller likewise. And suppose you have a monitor and you have a graphics card and which used to control the monitor. So likewise, for all the peripherals and all, you have a corresponding device controller will be there. Because all these devices are their characteristics, the nature of the device are different. Some are mechanical, some are semiconductor based, some of them are electromechanical, some of them are optical. So there are different nature by default. So therefore, for handling these devices and all, you have the respective device controllers will be there, right? These are the device controllers. And you have, this is your memory, main memory, right? This is the random access memory, main memory, semiconductor memory. And you have a processor here. And now here the communication between the processor and these devices and a memory and the devices to the memory, all these things will take place through a connected bus with which the data transmission or communication between the CPU and the other entities will take place. And the concurrent execution of CPUs and devices competing for the memory cycles. Yeah, right. Because you see that for all these devices and all, the memory, we have only one memory is available. Like there is a main memory. And here the data is available, the data will be placed or all your user programs to be executed that will be there in this main memory and all. And whatever the communication that takes place, that will be through memory only. So therefore, suppose the CPU want to access a particular variable from a keyboard, for example, then through keyboard, you can able to get that the variable value, and that value will be placed at a variable. That variable has certain address in the memory. So therefore, that value has to be placed in the main memory. Then from that main memory, the CPU will access that particular the variable value for its computation. So what I mean to say here is that actually here, so all these devices, all these entities will make use of the bus for accessing a memory and all. And in the process, there will be like a CPU and these devices, they can able to run parallelly. That means here the CPU processor inside, it may do some computation. And here in the same time, here these device controllers can have access to the data from the devices. Like for example, you have keyboard and where whenever the user press the key, for example, a particular character, and that the corresponding character will be loaded and placed and it's available at the controller and all here. And in the same time, in the meantime, actually during this time, the CPU is not idle. CPU will perform some other task. So likewise here, these the devices or device controllers are these I/O peripherals and the CPU, they can perform their execution concurrently. And again, these device controllers, as I mentioned here, so they contain the like they may contain the processor also. Some processing element also may present here, the device controllers. And along with that, there are some buffers will be there to store the data or to access the data from the devices into the controller or from controller to the devices also. So therefore, there will be some buffer registers and even the sometimes some processor also may present, right? So that way here the device controllers contains the some processing power and as well it contains some buffers also, right? And since there are processor and buffers they are present here, so therefore they can independently work. That means the CPU will do some job and the device controller will can able to carry out the job to interact with the devices, connected devices independently and all. So that way there will be some chance of concurrently they can able to perform, right? And to access the memory, then they should coordinate because the memory is a single unit and all of them should interact with the memory only through bus and all. Then there should be some coordinated way. These devices and the CPU should access the memory for exchange of data and other things. Yeah, here, as I mentioned here, the same thing here, it was given in the text form. I/O devices and CPU can execute concurrently, as I mentioned. And each device controller is in charge of a particular device type because, as I mentioned, because the devices are, the peripherals are of different nature, right? For example, you have a hard disk, for example, it contains like some like it contains both electrical aspects and mechanical aspects of that because there is a disk rotating the spindle and all, and there is a head and there is some magnetic properties. So all that way, like each device has its own characteristics. To deal with that, there is a specific controller, and with that controller, you can able to access the device. And the CPU moves the data from and to the main memory to the local buffers of the devices and all. Because the devices they cannot contact directly the memory and all. So whatever the devices want to either push the data into devices or receiving the data from the devices and all. So the CPU intervention is required, and with that they can able to carry out the data transmission or data transfer between the main memory and its corresponding peripherals. And IO is from device, IO from the device to the local buffer. Yeah, it means the device controller, right? So it means, as I mentioned, device controller and all here, the IO between the device and the device controller can takes place independently with the CPU. And then the device controller informs the CPU that it has finished operation by interrupt. Yeah, what it means here is that, for example, while you are executing some program and that program needs some data and the data is not available in the main memory, it requires some file. It has to open some file, it has to access the data, some file, and that file is not available in the main memory. So in that case, that file is there in the disk, in the hard disk. So therefore, you need to extract that file. You need to capture the data from that file, and then that file has to be brought into the main memory, and then you need to access the data. So for that, when the user program requests for a file data in the file, then that file is not, first it will try to contact memory. If it's not there, then the CPU will contact the disk controller. So how it will contact? The CPU will not directly contact. It will contact by using the operating system and all. Using operating system, it will first check the memory. The CPU directly check with the memory without operating system. But if it is not there, then the CPU will access the device controller using the operating system and all. So, for example, if the file is not present and file has to be brought in from the disk. So in that case, the CPU sends a request, or CPU use the operating system routine to send a request to the device controller, the disk controller, stating that a particular file has to be brought in. So then afterward, the CPU will not wait because for receiving the file from the disk controller, it takes time, reasonable amount of time. It's the order of milliseconds. Whereas the CPU and all, it functions or it executes or the way the CPU works will be in the order of nanoseconds. That means the clock cycles are of order of nanosecond. Because you see that the clock speed is in the form of gigahertz, like a 3 gigahertz, 2 gigahertz. It means that in a second you have a 2 into 10 power 9 clock cycles will be there. So for each clock cycle, maybe there is some unit amount of work will be carried out at the CPU. So, but to access a file from the disk and all, it is order of milliseconds. So there is a lot of change in the time, the speeds of the disk access versus the CPU execution. So therefore, the CPU will not wait for that. CPU will after pass on the task to the operating system, CPU will may perform some other job. So then the operating system will inform to the disk controller to do that job. Then the disk controller will fetch that particular file or a particular data, and then it will keep in the local buffer. And once the data transfer is over, because these two things can do parallel, because the CPU sends a request for file, and that file will be brought in from the disk to the disk controller, and during that time the CPU will do some other job. So here there is a parallel functionality, parallel computing. So one is the CPU will do its job, some other job, and here the disk controller will fetch the data from the disk, and then it will keep it ready at the disk controller, at the local buffer and all. So once this data transfer is over, then the disk controller will inform to the CPU saying that whatever the data you requested, so that data is now available at a local buffer, at the local buffer of a disk controller. And that informing the CPU will be by using, it will send after completion of data transfer from the disk to the disk controller. Then the disk controller will send a signal to the CPU. So, that signal is known to be interrupt. That signal is known to be interrupt, because the disk controller, whatever the job that was assigned, so that has completed, and that completed information will be informed to the CPU. Otherwise, the CPU doesn't know when it is completing. So that the disk controller, then it will send a signal to the CPU through an interrupt pin, and with that the CPU will realize that yeah, there is some device is requesting for something. So there is an interrupt. So that way, these peripherals and all, whenever they are carrying out certain tasks, and once that particular job is over, data transfer, whatever, then it has to inform to the CPU. So the way these peripherals will contact the CPU is nothing but through hardware. It will send a signal to the CPU, and that signal, the sending mechanism of signal to the CPU is known to be the interrupt and all. So whenever the CPU receives the interrupt, it means that the CPU will realize that immediately that yeah, there is some request from the peripherals. There is some request from the peripherals. So then the CPU is now executing some program, some other user program or some other program it's doing. Then CPU, whenever it receives interrupt, then the CPU first whatever the instruction is executing, so that particular instruction will be completed, and then the particular job, the particular program, whatever is executing, the entire status of the program will be placed in a memory. Status means the CPU when it's executing, it has CPU registers are there. It's doing some arithmetic operations or whatever it is. So the registers of the CPU may contain the information that is related to a current program. So now the interrupt has arrived. That means some peripheral has contacted the CPU to do some job. So now the interrupt has arrived. So when the interrupt arrives, then the CPU first it will stop the execution of the current program. That means whatever the instruction is executing, so it will just complete that instruction. Then afterwards, the process that is executing in the CPU, the currently, so that entire process state is nothing but the register, the contents of registers and other flags, whatever the status information of that related to that entire process will be stored in a kernel or in the memory, in the operating, in the part of operating system and all. So then then the CPU is now free from the execution. Now the CPU will find out actually which device has interrupted. Then based on that particular device, it will make use of the corresponding the operating system routine for carrying out the service to that particular device. Suppose, for example, this controller has sent the request. This controller has sent the signal. It means that now the interrupt is sent by the disk controller. So the CPU will know that yeah, the disk controller has sent the interrupt. So therefore, there will be corresponding interrupt service routine corresponds to the disk controller will be there. So that will be, so that is nothing but operating system program. It's an operating system code. So then the CPU will be run that particular operating system code corresponds to the disk controller, and that particular that is known to be interrupt handler or interrupt service routine. So that will be executed by the CPU, and in the part of that execution, then whatever the data that is there at the controller, so that will be passed on to main memory. So this will be this way. whatever the peripherals are sending a request and all. So those requests will be fulfilled. And once this data has been transferred to the main memory, then that means the interrupt service is over. That means now the disk controller, earlier the CPU has asked for, with respect to one program, it might have asked some some file to some data, data from certain file, maybe some 10 kilobytes or whatever. And now after receiving the data, disk controller will inform to the CPU. Then the CPU will, by making use of the interrupt service routine corresponds to the disk controller, then the CPU will transfer these 10 kilobytes to the in some memory location in the main memory. And later it will be used because for certain program it requires that 10 kilobytes. So because of that, that program has been stopped, right? And then then the CPU is executing some other program. And now during execution of other program, now the previous request, the disk controller has informed, the disk controller has sent a request interrupt. So now this has done. So after completion of this interrupt service routine, again the CPU will take up a job which was previously stopped. Because how it will do that? Upon end of this interrupt service routine, the interrupt service routine will place the contents of the process state, the previous process, wherever it was terminated. So that particular process state will be again loaded into the CPU. So now the CPU starts executing. So wherever the previous application was stopped. So that way the devices peripherals will contact the CPU, will perform their job, and that way the devices will communicate with the CPU and all. Right. So these things, the way of interrupts and other things and all, it will be discussed more clearly, more detailed way in your this one computer organization and all. But however, we will also discuss these interrupts and all in the later chapter. The next chapter also will try to come across these interrupts and all. So that time when this will be discussed 2-3 times, then you will get clarity on that. Okay, and so now, yeah, as I already mentioned here and all. Okay, done. Yeah, because here in the context of interrupt, we discussed this one. Interrupt is nothing but the devices or the peripherals, they interrupt the current execution of the CPU and all. Because whatever they are doing earlier, so that job has been done, that input operation or output operation, whatever that has been done. So that has to be informed to the CPU, then the CPU will take next course of action. Similar to that. It's not only the input, it's sometimes even output also. Sometimes, for example, you want to print something, for example. So in that case, you want to print so many pages. So in that case, the whatever to be printed, so that data has to be transferred from main memory to the printer controller. And the printer controller doesn't have enough buffer. It has some limited buffer. It may hold some 5 pages or 10 pages of data. So in that case, the printer controller, whatever the limited data it has, so it will be transferred from a main memory to the printer controller. Then the printer controller will send that data and it will get it printed. So once that whatever the 5 pages are over, then the printer controller will inform to the CPU, say that yeah, your job has been done. My buffer is free right now. So then the CPU again will transfer again another 5 pages from memory to this one using the interrupt controller, or you can say interrupt service routine and all. So that time the interrupt service routine will be different from the disk controller, because the printer here, whatever is using here, that particular controller, its nature is different. So therefore it uses. So therefore, depending upon the device and other things, it has the different types of interrupt service routines. So that depending upon the depending upon the device that is interrupted, it will make use of that particular specific interrupt service routine to perform the job. Yeah, right. Is it fine? Yeah, anyway, this interrupting and all we'll discuss, we'll reiterate that a bit later also in the slides and all. So in the first shot, you may not be very clear, but what you note here is that interrupt here means, in this context, interrupt here means it is interrupting the CPU. It's nothing but it is interrupting that is the peripherals are interrupting the CPU to take care of its functionality, to take care of the service and all. So that will be done by using operating system and all. because whenever the device controller, its local buffer is full, immediately just send the signal. It just send a pulse to the CPU. So whenever there is whenever there is a signal received at a particular pin of a CPU, then the CPU realizes that there is an interrupt. That means that one of the peripherals needs its service, right? Then it stops its execution, current execution. Then it handles then the OS will take over, and the interrupt service routine will be run. And again, upon completion of the interrupt service routine, then again the previous job will be loaded back into the CPU and it starts. So that way there won't be any problem in execution of the different applications over a CPU. Yeah. Then yeah, it's some more things on the related to the interrupt and all. So here, as I mentioned that a device may interrupt, like a peripheral may interrupt, right? So when a peripheral interrupt, there are as I already mentioned that we have based on the different nature of peripherals and all, you have, it's not that only one interrupt service routine, the same interrupt service routine may not be useful or may not be used. That depending upon the device, peripheral, or depending upon the task, you have a specific interrupt service routines will be there. So to discriminate them, you have the whatever the interrupt service routines are there. So these interrupt service routines will be numbered. Like for example, in a system to perform the different types of services for the device controllers, for the different peripherals and all, you may have, suppose for example, you have 100 different interrupt service routines are there. And then they will be numbered like 1 to 100 and all. And all those things are placed in the table, in the interrupt table. So in that interrupt vector means actually this interrupt vector contains the interrupt number, and that number is indexed to the table, interrupt table, where at that entry, at that particular index, you have the starting address of the interrupt service routine. It's not that the entire code is available. It's just the starting address of the interrupt service routine of the particular interrupt service routine will be present at that interrupt table, interrupt vector table and all. Then the CPU will be loaded that particular starting address and in its PC known to be program counter, and then the CPU fetches the data starting from that particular memory location, right? So that at that memory location, the corresponding interrupt service routine will be there. So there may be, for example, the hard disk controller, whatever the data that is fetched from the hard disk that need to be transferred to the memory. The corresponding interrupt service routine will be there at a particular memory location, and that memory location address will be placed against to that particular interrupt number and all. So that way the system, the operating system will maintain the interrupt vector where that depending upon the number of interrupts, unique interrupts and all, it just maintain the vector where that vector contains the number, like vector number and all. So then against to that number, it maintains a table and it points to index to that particular table for the given interrupt number. And at that number, at that location, you have the starting address of the memory of the first address of the interrupt service routine will be placed there. And now that will be accessed and that will be placed into the CPU, and CPU starts like fetching the instructions or fetching the data from the memory of that particular service routine. So that is what mean by the interrupt vector and all. Because you see that there are different devices are there, different peripherals are there. Like for example, you have a network adapter, then you have your keyboard controller, printer, display device, and several other things. So each of them you have to handle in a different way. So therefore, we have a specific service routines will be there, and for handling them, you have the interrupt vector is one way of doing that. It's nothing but it tries to discriminate that, and it provides the starting address of all these interrupt service routines in a tabular form, and then the CPU will fetch the corresponding interrupt service routine based on the address. Okay, and then the interrupt architecture must save this I have already mentioned. The interrupt architecture means whenever the interrupt arrives to the CPU, I already mentioned that whatever the present execution, whatever the current execution that is happening at the CPU, so that has to be saved in a memory, in some memory location, in a stack or in some memory location and all. And then afterwards, this interrupt service routine will take over the CPU and it will be executed. Then upon completion of the interrupt service routine, then whatever the previous instruction or whatever the previous job that is performing, it was stopped in between. So that particular status will be again brought in back to the CPU. That means the registers, all of them will be initialized with respect to that particular status. Then the CPU will execute that the previously stopped process wherever it was stopped. It starts from that again the next instruction onwards. So that's what here means the interrupt architecture must save the address of the interrupted instruction. That's what I mean by that. Then once the interrupt service routine starts executing, then it disable the other interrupts and all. Because you see that the nature of the CPU user, whenever the interrupt arrives, immediately it stops the execution of the current program or the current instruction, whatever it is. So if it is a normal user program, then whenever there is a request from the peripherals, it stops the user program and then it starts executing that particular interrupt service routine, or it starts performing the service of that particular peripheral. So this is carried out by the operating system. So when this is carrying out, there may be some other device, maybe parallelly receiving data or whatever. So that the job is completed, then that device may send the interrupt. So because already there is some interrupt is processing, interrupt service routine is processing, and again at that time the CPU should not be interrupted further. So that is the reason that if some interrupt is handling, some interrupt service routine is going on, at that time, even though other devices may be ready or may need the service of CPU, but they are not allowed to send the interrupt and all. They are not allowed to interrupt the CPU. So that's what I mean by the disable the all other interrupts to prevent to take care about the present interrupt and all. And so these are so far whatever I just mentioned, that is interrupting the CPU or like enabling the operating system, there is one way by all these hardware devices, all these hardware peripherals and all, right? So this is there is another way of stopping the execution of the current program, stopping the execution of current program. So that is known to be software generated interrupt and all. Software generated interrupt. So software generated interrupt means, so the chances of getting a software generated interrupt, software means it's a piece of code, it's a program, and the program has to generate the interrupt. So when it will generate the interrupt, only when it's execution only it can able to generate the interrupt. Otherwise, if the program is there in a memory, it's a passive one. It's a passive entity. It's nothing to do with that. There is nothing happens there. When the program starts execution, then it becomes active. Then it requires certain resources. It requires certain other entities to interact, communication, all these things happens when the program is in execution. So here the software generated interrupt means the interrupts will be generated during the program by the program execution. So it means that there is some program, user program, or maybe some whatever the kernel program, something is running on the CPU, and while running the program, this program generates the interrupt. So when it will do that, so it will do certain things. So sometimes, suppose when the program is executing, so during the execution, it encounters a computation like divide by 0, for example. It computes a division by 0. So at that time, when it tries to divide by 0 means, then it gives you it has to give value where it's not managed by the system and all. Then it has to raise the interrupt. It means that a program is executing and the program is about to do some malfunction, for example, divide by 0. So at that time, the program itself, that means when it tries to divide by 0, then at that time itself there will be like the program will be like interrupted, because when it tries to divide by 0, it will not happen. That means it cannot be represented, it cannot be handled. So therefore the currently executing program will be interrupted. Either it will omit that particular instruction or it starts from the next instruction onwards. First of all, it will display the user message saying that a division by 0 has been occurred, kind of a thing. So so here also CPU starts. So what happens is that during its execution, because in the execution current program itself, it's about to carry out or about to perform this division by 0, and that will be realized by hardware, and then it will be informed. It will be informed. That means it has to be taken care. So it will be taken care by the operating system and all. That means the kernel or operating system has to be taken care of that. Or some signal handler, some operating system handler has to be, service routine has to be taken care of that. So therefore, there is another way of generating the interrupts will be software generated interrupts. Earlier ones are known to be hardware generated interrupts. Hardware is nothing but the ones like peripherals, device controller, disk controller, printer controller, all this stuff. And now this is a software generated interrupt where when a program is in execution, when it tries to perform certain error by the user request, then at that time the program will be interrupted and it has to, and then the operating system will carry out service that particular interrupt and all. So the way it will do is that actually that means whenever it happen for all these software generated interrupts and all, it's known to be, it will be done by the trap. That means the trap is an instruction where whenever these things happens about to happen, then the system will the system will execute, then this trap will be generated. And trap is nothing but it just right now the user program is executing and now there is some malfunction is going to happen. Then with the help of trap instruction, then the operating system will take care of that to handle that particular the urgency, whatever it is. So this so that way the trap will generate in case of the software generated interrupts and all. And these software generated interrupts not only these small functions and all. Sometimes, for example, the user program is executing where the user needs the input from a keyboard. Like for example, when you write a C code, for example, you are taking the input, you are capturing input from the keyboard, right? So in that case, what to do? That means the user needs the input. The program requires the input from a keyboard, and it has to use that value for its computation in the CPU. Then the user program will not contact directly the IO device, right? So in that case, that means here the program requires the input from the keyboard, right? Or like for example, the program needs some input from the hello. 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 Yeah. Yeah. Hello. Somebody's. Yeah. Hello. Yeah. Yeah. Hello. Okay. Yeah. Let me finish in 5 minutes. You have maybe next class, maybe there. Where I am. Right. So yeah. Yeah, what I mean to software generated interrupts means like the way when the execution program require, one thing is that when some error happens and all, at that time the interrupt it has to be serviced, it has to be taken care by the in appropriate way. Like so sometimes actually these kind of errors and all managing these errors and all, they are also known to be exceptions. They are one and the same. We use the terms like exceptions and interrupts in a different way. Exceptions are basically these things like which are generated by software, right? And yeah, sometimes no, as I mentioned, the user program needs the input from the keyboard. Like for example, to perform certain thing, you need the input from a keyboard. So in a C program at a high level language, you write a scanf function to capture the input from the keyboard, right? So at that time also, the current program has to be interrupted because it expects the input from a keyboard. When it's executing, it expects the input from a keyboard. Then whenever the user enters that, then that will be captured, it will be used in its computation. So that way, so whenever the user program needs some IO, so that time also, so those interrupts are known to be software generated interrupts and all. Those interrupts are known to be software generated interrupts. So that way the software generated interrupts are like either the exceptions because of this division by zero or some other. Sometimes what happens when the user program, when it tries to fetch the data from a memory. So because of certain malfunction and all, the user tries to access the memory location which is not in his address space. Sometimes may happen. So because of that, at that time, whenever it tries to access some other memory location which is not intended for the particular user, at that time also the interrupts will be generated. Software generated interrupts will be generated. So that way you can say that the way the operating system will be functional in the event based. That means whenever there is some event occurs, then the operating system will come into the picture and it will run on the CPU and it will perform the desired service. Whether it may be from the user program point of view or it may be from the peripheral point of view also, right? So usually the peripherals, to provide a service of peripherals, it is known to be the terminology is the hardware generated interrupts, right? And whereas the user program, when it needs the IO, at that time, if it uses the the operating system routines, operating system functionality, it's known to be software generated interrupts and all. So that way, at any time, the operating system will come into the picture because of the interrupts, either due to the software interrupts or due to the hardware interrupts and all, right? So that way you can say that operating system is interrupt driven. So it means that the operating system will be functional or will be running on the CPU due to the interrupts. Either it may be hardware or software interrupts and all. So yeah, let us stop here at this point. And yeah, you can have, yeah, right. We have different ways of determining interrupts. As I mentioned, suppose the interrupt has arrived. How do you know that? What service routine I need to execute, right? So as I mentioned, that one way is that actually using an interrupt vector. So that means based on the device or something, it will just mention the numerical number. It indicates that a particular interrupt service routine number, or otherwise polling. Polling means actually here, suppose you have CPU received the interrupt, for example. So CPU is received the interrupt from the hardware devices. So it means that all the hardware devices are connected through bus, and through bus it receives the signal. So when it receives the signal, CPU will know that there is an interrupt request, but it doesn't know that actually which device has interrupted. So for that purpose, the CPU then will send back the signal, will poll the devices. That means it will just check with the devices which device is interrupted. So that way it will come to know that actually which device has interrupted, and accordingly the corresponding interrupt service routine can be executed. So that is known to be polling, right? So it just check that suppose you have n devices are there, then upon receiving the interrupt, then CPU will send the acknowledgement and will just check for just poll the devices, like which device requested for interrupt and all. So that way known to be polling. And other one is known to be vectored interrupt. Vectored interrupt means, as I mentioned, that the interrupt it contains the number, and that number, according to that number, there will be tabular will maintain, and then at that particular number, the corresponding interrupt service routines, the starting address will be there, and it will be executed. So yeah, I think yeah, we'll stop at this point of a time, and the next class will start from the like how the interrupts and CPU execution will takes in a timing diagram, which can able to explain and all. So we'll stop here, and the next week actually we have a class on Tuesday. We'll start as usual. And next week, I'll just conduct some mock test, because first time we are taking to you also to get familiar with that. And so we'll keep some test at 11:30, right? And the test is not counted for your grading process. But please, all of you attend that and take the test, get a feel for that, right? And I will also get the input from you, like, so that once you have done that one, later on, maybe the next class will be on 12th, right? And the next to next class is the 19th. So the 19th onwards, we have a regular test. And since you see that the class that is covered, whatever these 2 lectures and also that will be that will be evaluated and all. So that way it's not very difficult for you also. So please try to go through that quickly and then do the exam and all. Okay, so I'll stop here, and another thing is that maybe by the next week, I think all of you, I think more or less the class strength is also stabilized, and already I communicated through email and all. So as far as possible, you can discuss the general queries in the class itself. Let it, I can devote for 5 minutes or whatever. Generic queries like syllabus, that this and whatever generic queries used to handle through class itself. And most of that, and I will allot the TAs to you by dividing that into 4 groups. Like suppose you have 200 strength is there, I will split that into 4 parts, 50, 50, 50, and for each group, I will allocate 1 TA specifically for clarification of OS part and 1 TA for clarification of CA part. right? So that way for each group we have two TAs, and those TAs are one TA meant for OS, one TA meant for CA. So whatever you have queries, doubts, everything, and all, please first point of contact is that TA. You try to contact. I gave the mobile number also, and you try to contact him, get it resolved, because all the TAs are attending the classes also. So they will come to know, like they will know the what is happening in the class, in whatever the query you are asking, they can interpret the context, everything. So that way there is no issue at all. So please try to contact the TAs. Otherwise, no, you see, managing the 200 students, and even 10% of you raise the mails also, there will be 20 mails. So it will be very hard to answer or go through the mails and all. So as far as possible, please try to contact the TA, or otherwise in the class you can able to discuss, you can able to clarify the queries and all. Hmm? So that is one thing I just want to mention. So in the next class, I will give you the TA details and all. I already given maybe, but anyway, I'll give you the clearly which group, what TA and all that I'll give. And these slides and all I will upload in the here in the Teams and all. And you can also get these slides in the, I think they are in the, somewhere it's available on the net also. You can see. And the textbook and all, buy the book. It will be, it's a low price edition is available. And so that's all for today. So yeah, let's yeah, if you have anything quickly, or otherwise
Sir,
if
can
you
you
have
please
classes next,
mention
if you have
the
later,
course
yeah, if you have,
website on the
yeah,
chat
yeah,
box?
one minute, if you have later classes and all, so please leave the meeting. And others and all, if you have anything clarification on this, you may yeah, you can have that discussion for another couple of minutes. Yeah, somebody is asking actually.
Sir, can you please mention the course website on the chat box and also the book name?
Yeah, yeah, I'll do that.
Okay.
Maybe, yeah.
Thanks.
Yeah, right. I need to chat box. Okay. Course website is actually in the Teams itself. Actually, in the Teams itself, there is a file, no, like you have files are there. There is in that files folder, the course material will be there. In that, I will upload these slides. Hmm? And
Acha, okay.
and another thing is that the video part and all the whatever the video that was generated, that will be there in the website here in the Teams itself. I think that will be there for about 20 days. So you can able to download in the meantime whenever you are free. So you can have that video, the video content of this recording. And what else? And anyway, course website, I'm not again, I'm not mentioning, I'm not maintaining separately and all, because anyway we have Teams is there. And so in the Teams itself, under the files, class materials, you have the, maybe in the class materials, I will keep one folder like OS and all. So in that, whatever is there, everything I'll dump into that. You can able to see that. Okay.
Okay, thank you, sir.
And another thing, I don't know. So videos, I think you can able to download, right? You can able to do that, right? Yeah. And the book part, yeah, even the book also, I'll just I'll keep there. And uh, a book actually is the Galvino. They say that Galvino, and the other author name is that Silver Squads, operating system concepts. So anyway, I will give the details. Don't worry. Okay. Yeah. Hmm? Okay then. Yeah. 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 I'm leaving. Anybody have any queries? Yeah. I think I have to stop recording. No. Yeah.